Mercury is a world of extremes. A small, silent planet that races around the sun faster than any other, yet turns so slowly that a single day there lasts longer than its year. It is a place where heat and cold battle endlessly, where sunlight can melt metal while nearby shadows freeze harder than ice. Seen from Earth, Mercury appears as a bright, fleeting spark near dawn or dusk, vanishing quickly into the sun's glare as if it were shy of being seen. But up close, it is a world of deep craters, towering cliffs, and ancient scars that tell the story of a planet still shrinking as it cools. Named after the swift messenger of the Roman gods, Mercury lives up to its name, a restless traveler speeding through space, forever close to the sun yet wrapped in mystery. Though it is the smallest of the 8 planets, it remains one of the most challenging to study and to reach, holding its secrets tight behind a curtain of blazing light. To explore Mercury is to glimpse the solar system's beginnings, to see a world shaped by fire and time, and to understand how even the smallest planet can reveal the grandest truths about the universe. Mercury, the smallest planet in the solar system, holds a distinct place in the celestial family that orbits the sun. Though often overshadowed by its larger and more colorful siblings, this tiny world possesses a fascinating character shaped by its extreme conditions and proximity to our star. Mercury's small size belies its significance. It is a world of contradictions, blistering heat and freezing cold, relentless sunlight and profound darkness, stillness and motion. It is a planet that seems quiet and desolate from afar, yet its story reveals much about the origins and evolution of the solar system itself. At just over 4,800 kilometers in diameter, Mercury is only slightly larger than Earth's moon and smaller than some of the moons of Jupiter and Saturn. Despite its modest dimensions, it is surprisingly dense, with a large metallic core that makes up most of its mass. This dense interior suggests that Mercury once may have been a larger planet, stripped of much of its outer rocky layers by violent impacts or by the intense solar winds of the young sun. What remains today is a world that is at once ancient and scarred, its surface marked by countless craters and deep basins that tell a story written in stone and silence. Orbiting closer to the sun than any other planet, Mercury completes a circuit around our star in just 88 Earth days. This swift orbit earned it its name after the Roman messenger god who was known for his speed. Yet, while it races around the sun, it rotates very slowly on its axis, taking nearly 60 Earth days to complete a single turn. This peculiar relationship between its rotation and orbit produces long days and nights, during which the surface experiences extreme temperature shifts. On the side facing the sun, temperatures can soar above 400 degrees Celsius, hot enough to melt certain metals, while the night side plunges to nearly minus 180 degrees Celsius, colder than many regions of deep space. There is no atmosphere thick enough to retain heat or soften the transitions. Mercury's thin exosphere, composed mainly of trace gases like sodium and oxygen, cannot shield the planet from the brutal extremes of its environment. Looking upon Mercury's surface, one might think it a twin of the Moon. Both bodies are heavily cratered and ancient, remnants of a time when the inner solar system was a place of chaos and collision. The vast Caloris Basin, one of Mercury's most prominent features, is a crater more than 1,000 kilometers wide, formed by a cataclysmic impact billions of years ago. The shock waves from that collision deformed the crust on the opposite side of the planet, creating a landscape of twisted ridges and disrupted terrain. Elsewhere, long, sinuous cliffs known as scarps cut across plains and craters alike, evidence that the planet's core has cooled and contracted over time, forcing the surface to buckle as it shrank. Despite its harshness, Mercury is not entirely without mystery or beauty. In the perpetual shadows of its polar craters, where sunlight never reaches, scientists have discovered deposits of water ice, an astonishing find for a world so close to the sun. These icy reserves, preserved in the cold darkness, hint at the complex interplay of heat, impact, and time that has shaped the planet. Observations by spacecraft such as NASA's Messenger have revealed not only ice, but also strange hollows, bright, shallow depressions whose origins are still debated. In the grand architecture of the solar system, Mercury stands as a quiet reminder of beginnings. It is a world that has remained largely unchanged for billions of years, a survivor from the dawn of planetary formation. Its small size does not diminish its importance. Rather, it magnifies the wonder of its endurance. To look at Mercury is to see a relic of creation itself, a scarred, shining world racing endlessly through the light and shadow of the sun, carrying with it the memory of what the solar system once was and what, in many ways, it still is. Mercury, the innermost planet of the solar system, moves with a strange rhythm that defies what we might expect from a world so close to the sun. It races swiftly through space, completing a full orbit around the sun in just 88 Earth days, yet it turns on its own axis at a remarkably sluggish pace. One full rotation takes about 59 Earth days, and because of the way this slow spin interacts with its rapid orbit, a single day on Mercury, from one sunrise to the next, lasts about 176 Earth days. Time itself seems to move differently there, stretching and twisting under the influence of the sun's gravity. This slow rotation gives Mercury one of the most unusual day-night cycles of any planet. While Earth experiences sunrise and sunset within hours, Mercury's daylight lingers for months. When the sun finally rises over the rocky horizon, it does so against the blackness of space, for Mercury has no atmosphere to scatter the sunlight into blue. The dawn comes slowly, and as the sun climbs higher, it becomes a relentless presence. Its light grows so intense that it floods the barren plains and craters with blinding brilliance, heating the ground to temperatures of over 400 degrees Celsius. The landscape, scorched and silent, remains in daylight for weeks as the planet's slow spin inches the sun across the sky. Because Mercury's orbit is not a perfect circle but an ellipse, its distance from the sun changes throughout its year, and this creates a bizarre effect in the sky. Near certain points in its orbit, the sun appears to pause in its motion, even moving backward briefly before resuming its course. For an observer standing on Mercury's surface, the sun would seem to rise, stop, reverse direction for a time, and then set again. This extraordinary solar dance is the result of Mercury's slow rotation and the way the sun's gravity has locked the planet into a peculiar resonance. Mercury spins exactly 3 times on its axis for every 2 orbits, it completes around the Sun. This 3:2 spin-orbit resonance keeps the same regions of the planet facing the Sun at roughly the same times during each orbit, producing a rhythm that is both predictable and strange. The long Mercurian day also means that the contrast between day and night is extreme. Without a significant atmosphere to distribute heat, the surface undergoes brutal temperature swings. For months, the day side endures the blazing heat of unfiltered sunlight, while the night side, plunged into prolonged darkness, loses its warmth rapidly, falling to temperatures near -180 degrees Celsius. The transition between the two extremes happens slowly, but when it does, the shift is dramatic, a silent transformation from a world of fire to one of ice. This slow spin tells us something profound about Mercury's past. Astronomers believe that early in its history, the Sun's immense gravitational pull gradually slowed the planet's rotation, a process known as tidal locking. Over millions of years, the interplay of gravity and motion settled into the stable 3:2 resonance that persists today. This delicate balance has held for billions of years, ensuring that Mercury's strange day-night cycle remains unchanged even as the rest of the solar system evolves. To imagine standing on Mercury is to picture a sky ruled by patience. The Sun, huge and brilliant, would crawl across the horizon with agonizing slowness. Taking months to complete its arc, shadows would stretch and shrink almost imperceptibly, and time itself would seem to dilate. The stillness would be absolute. No wind, no clouds, no sound. Only the gradual movement of light and shadow over a surface that has remained nearly untouched since the dawn of the solar system. Mercury's slow rotation makes it a world of endurance, where change unfolds in slow motion and the passage of time is measured not in hours, but in seasons of light and darkness. Its rhythm, ancient and deliberate, reminds us that even among the planets, there is no single definition of a day. Each world spins to its own pace, and Mercury, nearest to the Sun yet moving with such patient grace, follows a cosmic tempo that is entirely its own. Mercury, the smallest and innermost planet of the solar system, moves with a swiftness that no other world can match. While Earth takes 365 days to complete its journey around the Sun, Mercury races through its entire orbit in only 88 Earth days. It is the sprinter of the solar system, darting around the Sun in a tight ellipse, completing 4 years in the time it takes Earth to finish just one. Its short year is both a testament to its closeness to the Sun and a window into the intricate gravitational forces that shape its motion. Orbiting at an average distance of about 58 million kilometers from the Sun, Mercury travels through space at nearly 47 kilometers per second, making it the fastest planet in the solar system. The laws of motion dictate that the closer a planet is to the Sun, the stronger the pull of gravity it feels and the faster it must move to stay in orbit. Mercury's speed is therefore a natural consequence of its position, but its small, swift orbit gives rise to many peculiarities. Because it circles the Sun so quickly, its seasons, if they can even be called that, are fleeting and difficult to define. The planet's path is not a perfect circle but an ellipse, and this shape means its distance from the Sun changes dramatically over the course of its year. At its closest point, called perihelion, Mercury feels the Sun's gravity at its strongest, and its velocity surges. At its farthest, or aphelion, the planet slows slightly, tracing a path that has been shaped and distorted by the immense pull of the Sun and the subtle influences of other planets. A year on Mercury passes so quickly that the concept of time there feels entirely alien compared to life on Earth. Yet, paradoxically, the planet's days are incredibly long. Mercury rotates very slowly, taking about 59 Earth days to turn once on its axis, and because of this, the relationship between its day and its year is deeply unusual. The combination of its slow rotation and rapid orbit means that from sunrise to the next sunrise, nearly 176 Earth days pass. In other words, one day on Mercury lasts twice as long as its entire year. For someone standing on its rocky surface, the sun would rise and set only twice during every orbit, a strange and mesmerizing rhythm dictated by cosmic mechanics. This short year and long day also produce remarkable phenomena in Mercury's sky. Because the planet moves so quickly in its orbit while turning so slowly, the sun appears to perform a curious dance. Near certain points in its orbit, as Mercury races around the sun, the star seems to pause in the sky, drift backward for a while, and then continue on its way. The sun's apparent motion, combined with its immense brightness and size from Mercury's surface, would create a sight of extraordinary intensity, a blazing, slow-moving fireball dominating a black sky, unfiltered by any atmosphere. Mercury's rapid journey around the sun has another consequence. It is constantly caught in a gravitational struggle that slightly alters its orbit with each revolution. This gradual precession of its orbit, its slow shifting in space, was one of the great puzzles of 19th century astronomy. It could not be fully explained by Newtonian physics until Einstein's theory of general relativity provided the answer. Mercury's short year and the minute variations in its path became key evidence that space and time themselves bend in the presence of gravity. Despite its speed, Mercury is a quiet and ancient world. Its surface, covered in craters and ridges, bears witness to billions of years of bombardment and stillness. The shortness of its year does not bring vitality or renewal as it does on Earth. Instead, it marks the endless repetition of a barren cycle. Seasons do not bloom there, only alternating stretches of heat and cold, light and shadow. And yet, in its swift orbit, Mercury reminds us of the elegance and precision of the solar system's design. Its 88-day year is a reflection of the perfect balance between motion and gravity, a dance performed so close to the sun that few could endure its intensity. Mercury's short year tells a story of motion, endurance, and harmony. A small planet moving swiftly through the light of creation, completing its silent revolutions with the timeless grace of a world forever bound to the sun's fiery heart. Mercury, the planet nearest to the sun, is a world of astonishing extremes. Among all the planets in the solar system, it experiences the greatest variation in temperature, a contrast so immense that it seems to defy logic. On its sunlit side, the surface blazes under relentless solar radiation, reaching temperatures high enough to melt lead. Yet just beyond the line where daylight fades into night, the heat vanishes, and the surface plunges into cold so deep that it could freeze most known substances solid. The difference between these two worlds of fire and ice can exceed 600 degrees Celsius, making Mercury a realm of both searing intensity and frozen stillness. This extraordinary temperature swing is a result of Mercury's unique combination of features: its closeness to the Sun, its slow rotation, and its lack of a substantial atmosphere. The planet lies less than 60 million kilometers from the Sun, receiving more than 6 times the solar energy that Earth does. When the Sun rises on Mercury's horizon, it floods the barren landscape with light so fierce that rocks glow with heat. The ground, made of dark basalt and silicate minerals, absorbs this energy and warms rapidly. As the Sun climbs higher in the black sky, there is no blue sky here, no air to scatter the light. The surface temperature can climb above 430 degrees Celsius. No living thing could survive under such conditions, and even spacecraft that venture too close must be protected with layers of heat-resistant materials. But Mercury's inferno is only half its story. Unlike Earth, which has an atmosphere to trap and circulate heat, Mercury's atmosphere is so thin it is almost non-existent. It consists only of trace amounts of elements such as sodium, oxygen, and hydrogen, forming what scientists call an exosphere. This tenuous veil cannot hold warmth or soften the transition between day and night. When the Sun sets on Mercury, an event that comes only after many long days, the heat escapes instantly into space. The surface radiates away its energy with no insulation to slow the process, and temperatures drop with astonishing speed. In the span of a few hours, the scorching daylight side becomes a frozen desert, with nighttime lows dipping to nearly minus 180 degrees Celsius. Paradoxically, despite being the closest planet to the Sun, Mercury is not the hottest in the solar system. That title belongs to Venus, whose dense carbon dioxide atmosphere traps heat in a runaway greenhouse effect. Mercury's lack of such an atmosphere spares it from that fate, but also condemns it to its extreme thermal cycle. This contrast reveals the delicate role that an atmosphere plays in moderating temperature, a balance that, on Earth, makes life possible. And yet, in the midst of this hostile environment, Mercury still surprises us. In the deep, permanently shadowed craters near its poles, where sunlight never penetrates, scientists have found deposits of water ice preserved by the eternal cold. These icy pockets, untouched for billions of years, coexist on a planet that elsewhere can rival a furnace. It is a striking symbol of the contradictions that define Mercury, a world of both fire and ice, of relentless heat and absolute cold. To contemplate its extremes is to glimpse the immense diversity of conditions that nature can create within a single small world, orbiting endlessly in the silent brilliance of the Sun. On Mercury, every step would feel strangely light. A person weighing 70 kilograms on Earth would weigh barely 27 there, their body seeming to float with each movement. The pull of gravity, that invisible force that binds everything to the ground, is only about 38% as strong on Mercury as it is on Earth. It is not because Mercury defies physics, but because it is so small and light, a world barely larger than Earth's moon, yet dense enough to surprise scientists with the strength of its grip. This lesser gravity shapes everything about the planet. How rocks crumble, how dust settles, how meteors strike, and even how the Sun would appear from its surface. Gravity is born from mass, and Mercury has less of it. It is the smallest of the 8 planets, with a diameter of just under 4,900 kilometers, barely 2/5 that of Earth. Its density, however, is unusually high. Much of Mercury's interior is made of metal, dominated by a massive iron core that takes up nearly 3/4 of the planet's radius. Despite that, the planet's total mass remains small compared to Earth's. The result is a gravitational field that is weak but steady, holding onto a thin veil of particles and dust yet unable to retain a true atmosphere. Because of this lighter pull, falling objects on Mercury descend slowly compared to Earth. A stone dropped from a hand would take longer to reach the ground, tracing a gentler arc through the still, airless space. The low gravity also means that craters from meteor impacts appear slightly different. When asteroids slam into the surface, debris flies outward farther and higher before settling back, forming long rays of ejected material that stretch across great distances. Mercury's landscape, pocked and wrinkled, owes part of its shape to how weakly the planet clings to its surface layers. If a person could walk there, their strides would lengthen almost effortlessly. A jump that might lift them 1/2 meter off Earth's ground could send them soaring 1.5 meters into Mercury's dark sky. Yet this freedom would come with an eerie sensation. There is no air to slow a fall, no wind to tug at clothing, no sound to accompany movement. The weak gravity combines with silence to create an otherworldly stillness, a quiet unlike anywhere on Earth. Even Mercury's relationship with the Sun is colored by its light gravity. The planet orbits so close to the Sun that it completes a revolution in just 88 Earth days. Yet its slow rotation and small mass mean that it cannot hold on to the gases that sunlight bakes from its surface. Hydrogen, helium, and oxygen escape into space almost immediately. The planet's gravity is simply not strong enough to keep them bound. What remains is an exosphere, a ghostly wisp of atoms continually blown away and replenished, a fragile trace of atmosphere that exists only because gravity allows it to linger briefly. The low gravity also reveals how extreme the contrast between Mercury and Earth truly is. On our planet, gravity shapes oceans, holds a thick atmosphere, and supports complex weather. On Mercury, gravity's gentler hand permits only a barren silence, a surface baked by heat and frozen by night. It is strong enough to keep the planet round, to pull down debris, and to hold its core together, but too weak to soften its edges with air or water. In a way, Mercury's gravity gives the planet its character. It is the reason the world feels both familiar and alien, a miniature version of Earth's structure played out under weaker rules. Standing there, a person might feel almost weightless yet deeply grounded, pulled toward a world that holds on lightly but refuses to let go completely. In that delicate balance lies Mercury's truth, a small planet with a firm heart and a gentle touch, circling endlessly in the sun's unrelenting light. Mercury is a world where the concept of seasons simply does not exist. On Earth, the familiar rhythm of spring, summer, autumn, and winter is created by the tilt of our planet's axis, which causes different parts of the globe to receive varying amounts of sunlight throughout the year. Mercury, however, spins almost perfectly upright. Its axial tilt is a mere fraction of a degree, about 0.03, so small that it is practically non-existent. Because of this, there is no shifting of sunlight, no gradual warming or cooling, and no transformation of the landscape with time. Mercury's environment is defined not by seasonal change, but by extremes that repeat endlessly: scorching heat under the sun and freezing cold in darkness. Instead of seasons, Mercury's weather, if one can call it that, is ruled by its proximity to the sun and its eccentric orbit. The planet travels in a highly elliptical path, which means that at certain points, it swings much closer to the sun than at others. When Mercury is near perihelion, the closest point in its orbit, the sun appears more than twice as large in its sky as it does at aphelion, the farthest point. This change in distance does affect the amount of solar energy Mercury receives, but not in a way that resembles seasonal variation. There is no atmosphere to moderate the temperature or to store heat from one part of the orbit to another. Each region of the planet experiences the same harsh cycle of blazing day and frozen night, again and again, with little variation over time. The absence of a meaningful tilt means that the sun's path across Mercury's sky is nearly the same every day of the Mercurian year. No part of the planet ever experiences long, gradual dawns or slanted winter sunlight like Earth does. When the sun rises, it does so abruptly, blazing against the blackness of space. Its light is unfiltered by air, falling directly on the dusty, cratered surface. Over time, the sun's rays heat the ground to temperatures above 400 degrees Celsius. When the slow rotation finally brings night, the warmth radiates away into space, and the surface chills to nearly minus 180 degrees Celsius. These extreme shifts repeat with mechanical precision, but they are not seasons in any earthly sense. They are the result of Mercury's slow spin and its lack of an atmosphere, not of axial tilt or changing sunlight angles. If one could stand at Mercury's poles, however, the story would be slightly different. Because the planet's axis is so nearly perpendicular, sunlight never rises high above the horizon there. Some craters near the poles remain in permanent shadow, their interiors never touched by sunlight since the planet's formation. Within these eternal pockets of darkness, spacecraft have detected deposits of water ice, an astonishing discovery for a world so close to the sun. The poles, cold and unchanging, are among the most stable environments in the solar system, a striking contrast to the fiery plains near the equator. Yet even here, there are no seasons, only unending cold and shadow, frozen reminders of how still Mercury's climate truly is. The lack of seasons gives Mercury an eerie timelessness. Its surface, scarred by billions of years of impacts, looks much as it did in the early history of the solar system. No wind, rain, or snow ever comes to alter the landscape. No spring thaw melts ancient frost, and no autumn dusk cools the stones. The only movement is the slow creep of sunlight and the expansion and contraction of rocks under the immense stress of temperature changes. In every direction, the terrain lies silent and unchanging, caught between fire and ice, light and darkness. To live on Mercury, if it were possible, would be to inhabit a place where time feels suspended. Days stretch endlessly under the glare of the sun, and nights descend into a stillness as cold as space itself. Without the comfort of seasons to mark the passage of time, life there would seem eternal and motionless, a repetition of the same extremes forever. Mercury's lack of seasons reminds us how unique Earth's gentle cycle truly is. It shows that the harmony we take for granted, the dance between tilt, orbit, and light, is a rare balance in a universe where most worlds, like Mercury, know only the relentless constancy of change without renewal. Mercury is a world that has been slowly shrinking for billions of years. Unlike the gas giants that expand with swirling storms and vast atmospheres, Mercury is a solid, rocky body whose very crust is being pulled inward by the cooling of its immense metallic core. This steady contraction has left visible scars across the planet's surface, towering cliffs, crumpled ridges, and twisted plains that tell the story of a world still evolving, even in its apparent stillness. Though the process unfolds on a timescale far beyond human perception, it is a reminder that even the oldest, most seemingly inert planets continue to change. When Mercury first formed more than 4.5 billion years ago, it was a much hotter world. Like all planets, it began as a molten mass, gradually cooling as it radiated heat into space. Beneath its thin, rocky crust lies an enormous iron core that occupies most of its interior. As this metallic heart cooled, it began to solidify and contract. Because Mercury's crust had already hardened, it could not stretch to accommodate the shrinking core. Instead, it fractured and folded, forcing great slabs of the surface to thrust upward and overlap each other. The result is a landscape crisscrossed by enormous cliffs called lobate scarps, some stretching for hundreds of kilometers and rising more than a kilometer high. These scarps are among the most striking features on Mercury's surface. They appear as jagged, curving ridges that slice through craters, plains, and mountains alike, showing that they formed long after most of the impacts that shaped the planet's crust. Their pattern is global, suggesting that Mercury's entire surface has contracted as the planet cooled. Scientists estimate that over time, Mercury's diameter has decreased by as much as 7 to 14 kilometers. A small change on a cosmic scale, yet massive when measured across a planet. For many years, it was assumed that Mercury's geological activity had ended billions of years ago. The planet, with no atmosphere, water, or tectonic plates, was thought to be geologically dead. However, data from NASA's Messenger mission, which orbited Mercury from 2011 to 2015, revealed otherwise. The spacecraft captured high-resolution images showing crisp, well-preserved scarps, some of which cut across small craters that appear relatively young. This means that the shrinking of Mercury is not merely an ancient event. It may still be happening today. The planet is cooling and contracting even now, continuing its slow inward collapse as its iron core loses the last of its primordial heat. This ongoing shrinkage has fascinating implications for understanding Mercury's internal structure and evolution. The planet's core remains partly molten, as evidenced by its weak but persistent magnetic field. The combination of a cooling core, a solidifying interior, and a brittle outer shell creates a dynamic, tension-filled environment beneath the surface. Each time the interior cools a little more, stress builds in the crust until it fractures and shifts. In this way, Mercury experiences a form of tectonic activity, not from the movement of plates as on Earth, but from the slow wrinkling of an entire planet. The shrinking of Mercury also offers insight into the behavior of rocky planets in general. Earth, Mars, and even the Moon show signs of similar processes, though on smaller scales. Studying Mercury allows scientists to see what happens when a planet's core dominates its structure and when time, gravity, and cooling work together to reshape it. The planet becomes a kind of fossil in motion, a record of the solar system's earliest history that still changes ever so slightly with each passing eon. To imagine Mercury today is to picture a silent world under relentless sunlight, its surface cracked and folded like the skin of an aging fruit. Every ridge and scarp marks a sigh of its shrinking core, a movement so slow it would take millions of years to notice. Yet, in that quiet contraction lies proof of vitality. Mercury is not merely a relic of the past. It is a living relic, still shifting and settling after billions of years. Its slow, steady shrinking is a testament to the enduring forces that shaped the planets long after their birth. A whisper of motion in a world once thought to be still. Mercury, the smallest planet in the solar system, holds a quiet but fascinating mystery within its metallic heart. It possesses a magnetic field, one that is weak, fragile, and yet unexpectedly alive. This discovery astonished scientists, for Mercury's size and age suggested that it should have long ago become a cold, inert world, incapable of generating such a field. And yet, despite being only about 1% as strong as Earth's, Mercury's magnetic field persists, a faint echo of internal motion within the planet's iron core. Its existence offers a window into the deep, unseen processes that still stir beneath the planet's ancient crust. A magnetic field is born from movement, specifically the movement of molten metal within a planet's core. On Earth, this churning motion of liquid iron and nickel creates a powerful dynamo effect, generating the invisible magnetic shield that surrounds the planet and protects it from the solar wind. For Mercury, the story is more complex. The planet is small, less than half the diameter of Earth, and should have cooled quickly after its formation. According to early models, its core ought to have solidified long ago, freezing the dynamo process and extinguishing any magnetic field. But when NASA's Mariner 10 spacecraft flew past Mercury in 1974, it detected something astonishing: a measurable magnetic field, faint but undeniable. Decades later, the Messenger mission confirmed and mapped this field in detail, revealing not only its weakness but also its asymmetry. The field is offset toward the planet's northern hemisphere, an odd displacement that hints at unusual conditions within Mercury's interior. To understand how this weak field endures, scientists turned their attention inward. Mercury's density is exceptionally high for its size, meaning that much of its interior is made of metal. An enormous iron core that occupies about 3/4 of the planet's diameter. Evidence suggests that at least part of this core remains molten, allowing convection currents to flow. These movements of liquid metal could sustain a modest dynamo, weak but persistent, that powers the magnetic field observed today. Some theories propose that light elements such as sulfur are mixed into the iron, lowering its melting point and keeping the outer core partly liquid even after billions of years. The weakness of Mercury's field is not its only remarkable feature. Because the planet orbits so close to the Sun, it is constantly bombarded by the solar wind, a stream of charged particles that interacts directly with its magnetosphere. This interaction creates a dynamic, ever-shifting space environment. Unlike Earth's strong, protective bubble, Mercury's magnetic field can be easily distorted or compressed by solar radiation. At times, the solar wind pushes so close that it touches the planet's surface, stripping away atoms from the thin exosphere and scattering them into space. Messenger's instruments detected frequent magnetic storms sweeping through Mercury's magnetosphere, miniature versions of those seen on Earth, but far more intense relative to the planet's size. This fragile magnetic field plays a key role in shaping Mercury's space environment. It creates a boundary that, though weak, still influences how charged particles from the Sun move around the planet. The interaction between the solar wind and Mercury's magnetic field produces bursts of high-energy particles and glowing auroral emissions at the poles, tiny, invisible flashes of light in a sky without air. Even in its weakness, Mercury's magnetism breathes life into the space surrounding it. The persistence of this field challenges assumptions about planetary evolution. It suggests that small worlds can remain geologically active far longer than once believed. Beneath Mercury's cratered and silent surface lies a world that still moves, still stirs, still remembers the heat and energy of its birth. The magnetic field it produces is not a relic, but a sign of endurance, the faint pulse of a metallic heart that refuses to die. To think of Mercury in this way is to see it not as a dead rock orbiting the Sun, but as a world with a living interior, fragile yet resilient. Its weak magnetic field, measured in mere fractions of Earth's strength, is a whisper of ancient power, a remnant of cosmic fire that still flickers after 4.5 billion years. In that whisper lies the story of a planet that, though small and battered, has kept its core alive against all odds. A quiet, magnetic survivor in the harshest realm of the Sun. Mercury, though the smallest planet in the solar system, hides within its compact frame one of the largest metallic cores relative to its size. Beneath its cratered crust and thin rocky mantle lies a massive sphere of molten and solid metal, making up nearly 3/4 of the planet's diameter. This immense core defines Mercury's structure, its density, and even its behavior in space. It is the reason the planet is so heavy for its size, why it has a magnetic field, and why its surface bears the marks of contraction. In many ways, Mercury is not just a rocky planet. It is a metal world, a remnant of the solar system's early, fiery beginnings. When scientists calculated Mercury's density, they were astonished. Despite being less than half the size of Earth, Mercury is almost as dense, suggesting that its interior must contain an unusually high proportion of heavy elements. Data from spacecraft like Mariner 10 and Messenger confirmed that the planet's metallic core makes up about 85% of its total radius, compared to Earth's core, which occupies only about 55%. Most of this metal is iron, with smaller amounts of nickel and lighter elements such as sulfur. The core itself is believed to be partly molten, surrounded by a relatively thin shell of rock only a few hundred kilometers thick. This means that Mercury is essentially a metal sphere wrapped in a thin crust, an exposed planetary heart still cooling from its creation. The question of how Mercury came to possess such a large core remains one of the great puzzles of planetary science. One theory suggests that billions of years ago, when the solar system was still forming, Mercury was struck by a massive object. The collision may have blasted away much of the planet's original outer rock layers, leaving behind a smaller but metal-rich remnant. Another theory proposes that intense solar radiation in the early days of the Sun's life evaporated the lighter materials from Mercury's surface, stripping the planet of its rocky mantle and leaving the dense metallic core intact. A third explanation is that Mercury formed in a region of the solar system where only the heaviest materials could condense, naturally producing a planet rich in iron and nickel. Whatever the cause, the result is a world that represents the dense inner building blocks from which all the rocky planets began. This metallic core is not just a structural feature. It also powers Mercury's magnetism. Against all expectations, Mercury possesses a magnetic field, though it is only about 1% as strong as Earth's. Scientists believe it is generated by the slow movement of molten iron within the planet's outer core. This dynamo effect produces a weak but measurable magnetic field that interacts with the solar wind, creating a small magnetosphere around the planet. The persistence of this field shows that Mercury's interior has not yet fully cooled and solidified. Deep beneath its quiet, cratered surface, there is still motion, a faint stirring of metal that keeps the planet alive in a subtle magnetic way. The influence of the metallic core can also be seen on Mercury's surface. As the planet's interior has cooled and contracted over billions of years, the shrinking core has caused the crust to wrinkle and fold. This process has produced enormous cliffs known as lobate scarps, which stretch for hundreds of kilometers and rise up to a kilometer high. They are visible reminders of the slow, steady contraction of a planet still shaped by the cooling of its great metallic heart. To imagine Mercury is to picture a world of extremes, a dense, heavy sphere of metal orbiting close to the sun, bathed in light and shadow. Its thin rocky shell hides an inner world that still moves and breathes, radiating the last heat of its birth. In that molten core lies the key to Mercury's density, its magnetic field, and its evolution. More than any other planet, Mercury is defined by what lies beneath its surface. An immense metallic heart that continues to beat, slowly and silently, at the edge of the sun's eternal fire. Mercury bears a surface that tells a story of violence and endurance. From afar, it looks strikingly similar to Earth's moon, gray, barren, and pocked with countless craters. Every inch of its landscape speaks of ancient impacts, the scars of a time when the inner solar system was young and chaotic. Meteorites and asteroids, left over from the formation of the planets, once roamed freely through space, colliding with anything in their path. Mercury, with its thin atmosphere and proximity to the sun, had no protection from these assaults. The result is a world whose face remains frozen in time, a living record of 4 billion years of cosmic history. The craters on Mercury vary dramatically in size and character. Some are tiny pits no larger than a pebble, while others are vast basins hundreds of kilometers across. The most famous of these is the Caloris Basin, a colossal impact crater nearly 1,550 kilometers in diameter, large enough to fit much of Western Europe inside it. The collision that formed Caloris was so powerful that it sent shockwaves rippling through the entire planet. On the opposite side of Mercury, these waves met and interfered with one another, producing a chaotic region of twisted hills and ridges known as the Weird Terrain. This strange landscape stands as silent evidence of the unimaginable forces that once shaped Mercury's surface. Over billions of years, countless smaller impacts added their marks. Because Mercury has no atmosphere thick enough to burn up incoming meteoroids, every object that strikes its surface leaves a lasting impression. There are no winds to erode the craters, no water to wash them away, and no plate tectonics to recycle the crust. Once an impact occurs, its trace remains for eternity, unless another strike happens to overlap it. Some craters are crisp and bright, their rims sharp and their ejecta blankets still visible signs of relatively recent impacts in geological terms. Others are so worn and softened by time that they blend into the surrounding plains, ancient wounds that have been partially filled by later lava flows. These smooth plains, which spread across parts of Mercury's surface, hint at another chapter in the planet's history. After the era of heavy bombardment, volcanic activity reshaped portions of the crust. Lava poured out from fissures, flooding low-lying regions and burying some older craters. The result is a patchwork world, part ancient and cratered, part resurfaced and smoothed by volcanic forces. Even so, the evidence of impacts dominates everywhere, making Mercury one of the most heavily cratered bodies in the solar system. The surface tells not only a story of violence but also of endurance. Because Mercury's environment has remained almost unchanged for billions of years, its craters serve as a kind of archive of the early solar system. Scientists can study their distribution, depth, and layering to understand the rate of impacts and the conditions that prevailed when the planets were still forming. Each crater is like a page in an ancient record, offering clues about the materials that collided with Mercury and the internal structure of the planet itself. The landscape of Mercury is also shaped by other geological features that intersect with its craters. Long cliffs called scarps snake across the surface, sometimes cutting through ancient impact basins. These scarps were formed as Mercury's core cooled and contracted over time, causing the crust to buckle and fold. The fact that they slice through old craters shows that Mercury is still, in a sense, a dynamic world, even if its changes unfold over immense spans of time. To stand on Mercury would be to see a landscape untouched by life, weather, or time as we know it. The horizon would be jagged with crater rims and ridges, the ground strewn with boulders thrown up by ancient impacts. Under the harsh light of the sun, the surface would shimmer with dust and rock, utterly silent yet heavy with history. Every crater would be a reminder of the solar system's turbulent youth, when chaos reigned and planets were shaped by collision and fire. Mercury's heavily cratered surface is more than a mark of destruction. It is a monument to survival. It has endured the violence of creation and emerged as a testament to the enduring forces of nature. Its face, scarred and steadfast, reveals the story of a planet that has not forgotten its beginnings, a world that holds within its craters the memory of everything that has passed since the dawn of the solar system. Mercury exists in a realm of constant assault from the solar wind, a powerful stream of charged particles that flows outward from the sun at tremendous speeds. Unlike Earth, which is protected by a thick atmosphere and a strong magnetic field, Mercury stands almost naked against this relentless bombardment. The planet's small magnetic field and thin exosphere offer little defense against the waves of solar radiation and energetic particles that strike its surface every day. This unending exposure has shaped Mercury's appearance, its environment, and even its chemistry, carving the marks of the sun's fury into its rocky skin. The solar wind is composed mainly of electrons, protons, and helium nuclei that race outward from the sun at hundreds of kilometers per second. When these particles reach Mercury, they interact directly with the planet's magnetic field and surface. Mercury's magnetic field, though real, is much weaker than Earth's, only about 1% as strong, and it is offset from the planet's center, making one hemisphere more exposed than the other. As the solar wind collides with this fragile magnetosphere, it distorts it into a teardrop shape, squeezing it on the side facing the sun and stretching it into a long tail behind the planet. This magnetic tail, known as the magnetotail, flutters and twists as streams of solar particles flow past, constantly reshaping the invisible shield that surrounds Mercury. Because Mercury's atmosphere is almost non-existent, only a whisper of gas particles called an exosphere, the solar wind has direct access to the surface. When high-energy particles crash into the ground, they knock atoms loose, launching them into space or into temporary orbit around the planet. This process, known as sputtering, continually strips material from Mercury's crust and feeds its exosphere with elements like sodium, potassium, calcium, and magnesium. Observations have even revealed glowing trails of these elements in Mercury's thin atmosphere, shining faintly in the sunlight as they are carried away by the solar wind. The bombardment also darkens the surface over time, chemically altering the minerals and leaving behind a coating of space-weathered dust that dulls the planet's reflection. The interaction between the solar wind and Mercury's magnetic field is a dynamic and violent process. Magnetic reconnection, when magnetic field lines break and reconnect, occurs frequently, unleashing bursts of energy that accelerate particles and send them crashing into the surface. These events can generate intense auroras near Mercury's poles, similar in principle to Earth's northern and southern lights, but invisible to human eyes. Instead of shimmering skies, Mercury's auroras are flashes of X-rays produced when solar particles slam into the surface at tremendous speeds. Every moment, the planet's magnetosphere is alive with motion, expanding and contracting in rhythm with the changing flow of the solar wind. Messenger, the spacecraft that orbited Mercury from 2011 to 2015, observed this interplay in remarkable detail. It detected how solar storms, massive eruptions of charged particles from the sun, could overwhelm Mercury's magnetic field, forcing it to collapse temporarily and allowing solar wind to strike the surface directly. During these storms, radiation levels soar, and the planet's already fragile exosphere is dramatically altered. Sodium and other elements flare in brightness, carried away into long tails that trail behind the planet like a comet. This constant exchange between surface, space, and sun makes Mercury a living laboratory for studying how planets endure the harshest conditions near a star. Over billions of years, this bombardment has shaped Mercury into a world of scars and shadows, a place where the sun's power is both creator and destroyer. The solar wind strips and sculpts, revealing a surface baked and battered, a world that never truly rests. Yet, in its endurance, Mercury tells a story of resilience. Despite being battered by radiation and particles, it continues to orbit faithfully around its parent star, reflecting sunlight with the calm brilliance of a survivor. Its surface may be silent, but every atom bears witness to the fierce winds of the sun that sweep across its face, endlessly carving the character of this smallest and most enduring world. Mercury, though one of Earth's closest planetary neighbors, is among the most difficult planets to observe. It shines brightly when visible, but the opportunities to see it are fleeting, and the conditions are rarely ideal. Its elusive nature is a consequence of its position in the solar system. Mercury is the innermost planet, orbiting so close to the sun that it never strays far from the dazzling glare of daylight. From Earth, it can only be glimpsed during brief moments near sunrise or sunset, when the sun is just below the horizon and Mercury hangs low in the sky. For most of its orbit, it is lost in the brilliance of the sun's light, hidden from view. Unlike Venus, which also orbits close to the sun but rises high enough above the horizon to be a familiar morning or evening star, Mercury remains closer to the sun's edge. It never appears more than about 28 degrees away from it in the sky. This means that, even at its farthest separation, it is always drowned in twilight, hovering over the horizon for just an hour or so before vanishing into the glow of dawn or dusk. For much of the time, it is completely invisible to the naked eye, either because it is too faint or because it is lost in the daylight sky. Astronomers throughout history struggled to find it, often relying on precise calculations to predict its brief appearances rather than direct observation. When Mercury does appear, it can be striking, a tiny golden point of light shimmering against the fading colors of the horizon. Ancient astronomers knew of it but found it mysterious. The Babylonians and Greeks both recorded observations, though they believed they were seeing two different stars, one that rose before the sun and another that followed it after sunset. The Greeks named these two appearances Apollo and Hermes, not realizing they were the same planet seen at different times. It was only later that astronomers understood that this elusive wanderer was a single body, orbiting close to the sun in a tight, rapid path that brings it around every 88 Earth days. Even with modern technology, Mercury remains a challenge to study from Earth. Observing it through telescopes requires careful timing and location. The planet's proximity to the sun means that it is often best viewed during twilight, when the contrast between sky and planet is high enough to make it visible. But these same conditions create difficulties. The atmosphere near the horizon distorts light, blurring details and causing the image to shimmer. Astronomers must also take precautions to avoid pointing telescopes too close to the sun, which can damage equipment or even eyes. As a result, Mercury's surface details are nearly impossible to see clearly from Earth. For centuries, its true nature, a cratered, barren world remained unknown. Only with the advent of space exploration did Mercury's secrets begin to unfold. The Mariner 10 mission in the 1970s and the Messenger mission decades later provided the first detailed images, revealing a planet scarred by impacts and shaped by contraction. These spacecraft filled in the gaps that ground-based observation could never bridge. Even today, most of what we know about Mercury comes not from telescopes on Earth, but from the eyes of machines that ventured close enough to pierce the glare of the sun. For amateur observers, glimpsing Mercury remains a small triumph, a fleeting sight of a planet that hides in plain view. It appears for only a few weeks at a time, alternating between morning and evening skies depending on its orbit. To see it, one must look to the right place at the right time, often just before dawn or just after sunset, when the world is quiet and the sky glows faintly. Those who have seen it often describe a feeling of discovery, of catching a glimpse of something rare and elusive. In this way, Mercury's difficulty of observation has shaped its mystery. It is a world that reminds us how much can hide in brightness, how even the closest of neighbors can escape easy notice. For as long as people have watched the heavens, Mercury has been the quiet companion of the sun, visible only in the edges of light, fleeting and secretive, a planet that reveals itself only to the most patient eyes. Mercury holds an unexpected distinction. It is the second densest planet, surpassed only by Earth. This surprising fact reveals much about its internal structure and its turbulent past. Though it is barely a third the size of Earth, Mercury's average density rivals that of our own planet, suggesting that it is made mostly of metal. Beneath its thin crust and rocky mantle lies an enormous iron core that dominates the planet's interior, making up about 3/4 of its diameter. No other planet, relative to its size, is so filled with metal. The story of why Mercury is so dense is a mystery that leads deep into the history of planetary formation and the violent processes that shaped the early solar system. A planet's density is a measure of how much mass is packed into a given volume, and for Mercury, that value is extraordinarily high, about 5.4 grams per cubic centimeter, compared to Earth's 5.5. On Earth, this density arises partly because gravity compresses the materials in its interior. Mercury, being much smaller, does not experience such strong gravitational pressure. Therefore, its high density must come from its composition, not compression. This means Mercury is made largely of heavy elements, primarily iron and nickel, while its outer rocky layers are relatively thin. Scientists believe that Mercury's metallic richness can be explained by several possible origins, each painting a vivid picture of planetary evolution. One theory suggests that Mercury once was a larger planet with a thick mantle of rock similar to Earth's. In the chaotic early solar system, however, immense collisions between young planets and debris were common. At some point, Mercury may have been struck by a massive object that stripped away much of its outer layers, leaving behind a smaller, metal-rich core. What remains today would then be the dense heart of a once larger world, exposed and scarred. Another theory proposes that intense heat from the young sun vaporized much of Mercury's lighter material. In this view, the solar radiation was so strong that the upper layers of rock were blasted away or prevented from condensing during formation, while the heavier metallic elements remained. Either way, Mercury emerged as a planet dominated by metal, a tiny, compact survivor from a time when the inner solar system was still taking shape. The structure of Mercury supports these ideas. Its immense iron core, still partly molten, makes up more than half of its total mass. Above it lies a relatively thin silicate mantle and crust, scarred by countless craters and ridges. This metallic interior not only accounts for Mercury's high density, but also helps explain its magnetic field. Despite its small size, Mercury's core remains active enough to generate a weak magnetic field through the slow movement of its liquid metal layers. This is a remarkable feature for such a small planet, one that further underscores the dominant role of metal in its composition. Mercury's density also influences its surface and geological features. As the core cooled and contracted over time, it caused the outer crust to wrinkle and buckle, forming long cliffs known as lobate scarps that stretch for hundreds of kilometers. These cliffs are physical evidence of a shrinking planet, one whose dense metallic heart continues to shape its face billions of years after formation. In a way, Mercury's density is its defining trait, the secret to its endurance and identity. It makes the planet not just small and heavy, but ancient and revealing. By studying Mercury, scientists gain insight into the earliest conditions of the solar system, the materials that condensed near the sun, the violence of planetary collisions, and the evolution of metal-rich worlds. Though often overlooked, Mercury carries in its dense, compact body the memory of creation itself. To imagine Mercury is to picture a world that has shed all but its essence. It is the bare, gleaming core of a planet, stripped to its heart, orbiting close to the sun like a survivor of cosmic fire. Its weight speaks not of size but of substance, a quiet testament to the forces that forged it and to the enduring strength of metal in the story of worlds. Mercury is a world where time and motion play strange tricks. Among its many peculiarities, one of the most fascinating is that, in some places, the sun appears to rise, stop, reverse course, and then rise again, or set, reverse, and set once more. These double sunrises and double sunsets are not illusions, but real phenomena caused by Mercury's unique combination of orbital speed and rotational period. On this small, sun-scorched planet, the dance between day and night follows rules that defy ordinary experience, creating a sky where the sun itself seems to change its mind. To understand this rare spectacle, one must look at how Mercury moves. The planet travels around the sun in just 88 Earth days, the shortest year of any planet. Yet it rotates very slowly on its axis, taking about 59 Earth days to complete one full spin. Because of this strange balance, a single solar day on Mercury, the time between one sunrise and the next, lasts 176 Earth days. This means that while Mercury spins slowly, it races around the sun so quickly that its orbital motion nearly cancels out its rotation for long stretches of time. The result is that the sun's movement across the sky slows, halts, and even reverses direction before resuming its course. This reversal happens because Mercury's orbit is not a perfect circle but an elongated ellipse. As the planet moves closer to the sun, reaching a point called perihelion, it speeds up in its orbit due to the sun's stronger gravitational pull. However, its rotation speed stays the same. Near perihelion, Mercury's orbital motion temporarily overtakes its rotation. For an observer standing on the planet's surface, the sun would appear to rise as usual, climb slightly above the horizon, then pause. As Mercury moves faster in its orbit, the sun would seem to move backward, dipping once again below the horizon before rising a second time. The same happens in reverse near sunset. The sun might sink toward the horizon, stop, rise briefly, and then finally disappear. Imagine standing on Mercury during such an event. The landscape around you would be stark and silent, gray plains of rock and dust stretching beneath a sky without air. The sun would appear more than twice as large as it does from Earth, blazing with unbearable intensity. At dawn, its upper rim would emerge over the jagged horizon, flooding the surface with fierce light. Then, as the planet's orbital speed increases, the sun would hesitate, its motion slowing until it begins to drift backward. Shadows would lengthen again, and darkness would creep across the land, only for the sun to surge forward once more, blazing into the sky for the second time. The reversal could last hours or even days, depending on your position on the planet, because of Mercury's 3:2 spin orbit resonance, meaning it rotates 3 times for every 2 orbits around the sun. This phenomenon does not happen everywhere at once. Some longitudes experience the double sunrise, while others experience a more conventional day-night cycle. If a person could somehow endure the planet's extreme heat and cold, they would witness a solar performance unlike any other in the solar system. A sun that moves in slow, deliberate rhythms, reversing and resuming its course as though time itself were breathing. These double sunrises and sunsets also affect Mercury's surface temperatures, which vary more than those of any other planet. During the long, drawn-out daylight, parts of the surface can reach 430 degrees Celsius, while during the equally long night, they plunge to -180 degrees. The prolonged exposure to sunlight and darkness, compounded by the sun's peculiar motions, creates a cycle of heating and cooling that has shaped the planet's crust and possibly influenced the behavior of its thin exosphere. For centuries, Mercury's motion puzzled astronomers, who could not reconcile its orbit with simple celestial models. Only with modern understanding of orbital mechanics and relativity did the full picture emerge. Today, we know that Mercury's double dawns and dusks are the natural result of its gravitational bond with the Sun, a consequence of its elliptical orbit and resonant rotation. On Earth, the Sun's path is predictable, steady, and rhythmic. On Mercury, it is anything but. There, the Sun dances, a fiery performer pausing and bowing before continuing across the heavens. The double sunrise and sunset are reminders of how different and how wondrous the universe can be when seen through the lens of another world. Mercury seems an unlikely place to harbor anything as delicate as water ice. It circles so close to the sun that its dayside can reach temperatures above 400 degrees Celsius, hot enough to melt lead. For centuries, scientists assumed it was a world completely parched, scorched by unrelenting sunlight and incapable of preserving even a trace of water. Yet, in one of the solar system's most surprising discoveries, evidence has revealed that Mercury may indeed possess water ice. locked away in the shadows of its north and south poles. This paradox exists because of Mercury's unusual geometry and its nearly upright rotation. The planet's axis is tilted by less than 1 degree, which means that sunlight strikes its poles at a very shallow angle. As a result, some craters near the poles have floors that never see sunlight at all. These regions, known as permanently shadowed craters, remain in perpetual darkness, shielded from the searing heat that scorches most of Mercury's surface. Temperatures in these shadowed pockets can drop below -170 degrees Celsius, cold enough for water ice to remain stable for billions of years. The first hints of this hidden ice came in the early 1990s from radar observations made on Earth. Scientists using powerful radio telescopes detected bright, reflective patches near Mercury's poles, signals similar to those observed from icy regions on Mars and the icy moons of Jupiter. At first, the findings were met with skepticism. Could water really exist on a planet so close to the Sun? But later, NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed the suspicion. Using neutron spectrometry and thermal mapping, Messenger detected strong evidence of water ice deposits buried beneath thin layers of dark, carbon-rich material. These dark coatings may be remnants of organic compounds delivered by ancient comets or asteroids, which also could have supplied the ice itself. The discovery of water ice on Mercury transformed the way scientists understood the planet. It revealed that even in the most inhospitable environments, there are places where the right conditions can preserve something precious. The poles of Mercury are like natural freezers, untouched by sunlight and sealed by cold. Over billions of years, as comets and meteoroids bombarded the inner solar system, they likely brought water and other volatile substances. Most of these materials would have evaporated immediately under Mercury's intense heat. But in the deep shadows of the polar craters, some of the water may have settled and remained, hidden away from the sun's glare. The presence of ice on Mercury also raises intriguing questions about how water is distributed throughout the solar system. It suggests that ice is far more widespread than once believed, existing even on worlds that seem impossibly dry. The conditions that preserve ice on Mercury's poles might also exist on other airless bodies, such as the Moon, which has its own permanently shadowed craters. Both worlds show that sunlight, or the lack of it, can play as decisive a role in shaping a planet's environment as its distance from the Sun. If one could stand at Mercury's north or south pole, the scene would be stark and silent. The sun would never rise above the crater rims. The sky would remain pitch black even as sunlight struck the peaks above. Within the shadowed depressions, the ground would glimmer faintly, perhaps coated with frost or buried beneath a thin layer of dust. The airless stillness would preserve this fragile ice indefinitely, untouched by wind, water, or warmth. In the grand story of the solar system, Mercury's polar ice serves as a reminder of nature's ability to find balance even in extremes. It is a symbol of endurance, a trace of water surviving on a world that endures both the sun's fiercest heat and the coldest shadows of space. In those frozen craters, untouched since the dawn of the solar system, Mercury holds a quiet secret: that even the most unlikely places can shelter the building blocks of life, hidden in the eternal darkness at the edge of light. Among Mercury's many strange and beautiful features, few are as intriguing as its hollows, bright, irregular depressions scattered across its cratered surface. These hollows are unlike anything seen elsewhere in the solar system. They shimmer with a pale brightness against the planet's dark, weathered crust, as though newly exposed and untouched by the aging effects of space. Their discovery by NASA's Messenger spacecraft in 2011 was one of the most surprising findings about Mercury, revealing that even this small, airless, and ancient world is still geologically active in subtle but fascinating ways. Hollows are not impact craters, nor are they volcanic vents. Instead, they appear as clusters of shallow pits, some just a few meters deep, others stretching for several kilometers, often found on the floors or central peaks of larger craters. Their edges are irregular and sharp, showing no sign of erosion. Most are surrounded by bright halos, suggesting they are relatively young and have not yet been darkened by the harsh bombardment of solar wind and micrometeoroids. What makes them especially interesting is that they seem to form by the loss of volatile materials, substances that vaporize easily when heated or exposed to space. Before Messenger's mission, scientists assumed Mercury was geologically dead, its surface frozen in time for billions of years. The discovery of hollows challenged that idea. The leading theory is that hollows form when volatile elements, buried within surface rocks, are released into space. Mercury's crust, rich in sulfur, sodium, potassium, and other volatile materials, is constantly bombarded by solar radiation and micrometeorites. When this energy penetrates the surface, it can cause these materials to sublimate or vaporize, leaving behind empty spaces. The overlying rock then collapses, creating depressions. This process may still be ongoing today, meaning Mercury continues to change, however slowly, under the fierce gaze of the sun. Messenger observed hollows in many places across Mercury, but they are particularly common in and around impact craters. The impacts that created these craters likely brought buried volatile-rich material closer to the surface, where it could later be exposed. In some cases, hollows appear on the peaks and ridges of central crater mountains, regions that were thrust upward by the immense force of the impact. These elevated hollows suggest that the process is not confined to lowlands or shaded regions. It can occur anywhere volatile-rich rock lies near the surface. The fact that hollows have been found on nearly every part of the planet implies that Mercury's volatile elements are widespread, embedded deeply throughout its crust. One of the most famous examples is in the large crater Cortez, where brilliant, glowing hollows sprawl across the crater floor, gleaming like patches of frost in the sunlight. Similar formations have been observed in craters such as Radatladi and Tyagaraja, each offering clues to Mercury's chemical makeup and internal processes. The bright coloration of these hollows may result from freshly exposed minerals that have not yet been darkened by space weathering. Over time, the constant bombardment of particles from the sun will gradually dull their brilliance. But because so many hollows remain bright, it suggests they are geologically young and possibly forming even now. The discovery of hollows also deepens the mystery of Mercury's formation. For a planet so close to the sun, it should have lost its volatile elements long ago. Yet the presence of hollows indicates that Mercury not only retained them but continues to release them. This contradiction challenges conventional models of planetary development and points to a more complex early history, perhaps one involving cooler formation conditions or an origin farther from the Sun. In the end, Mercury's hollows are a symbol of vitality in an otherwise desolate world. They show that the planet, despite its age and size, is not merely a fossil of the early solar system but an evolving body, shaped by ongoing processes that reveal both its past and its present. The bright, delicate hollows scattered across Mercury's rugged face are silent reminders that even the smallest and most sun-scorched planet still breathes, changing imperceptibly beneath the constant blaze of its parent star. Mercury defies expectations in many ways, and one of its most surprising traits lies in the chemistry of its surface. When scientists first began to analyze Mercury's composition, they expected it to be depleted in volatile elements, those that easily vaporize at high temperatures, because of the planet's proximity to the Sun. In the intense heat of the early solar system, volatile materials should have boiled away, leaving behind only the most refractory or heat-resistant substances like iron and silicates. Yet, to the astonishment of researchers, data from NASA's Messenger spacecraft revealed the opposite. Mercury's surface is rich in sulfur and other volatile elements such as sodium, potassium, and chlorine. This discovery reshaped our understanding of how the planet formed and evolved, challenging long-held assumptions about the effects of solar heat and planetary formation near the Sun. Sulfur, in particular, is found on Mercury in much higher concentrations than on any other rocky planet. Messenger's X-ray and gamma-ray spectrometers detected sulfur abundances up to 10 times greater than those on Earth, Mars, or the Moon. Such a finding was unexpected, because sulfur is a volatile element that should not survive the high temperatures thought to exist near Mercury's birthplace. Its presence implies that Mercury either formed under cooler conditions than previously assumed, or that it somehow retained these materials despite the Sun's intense radiation. This abundance also hints that Mercury's interior chemistry differs dramatically from that of other terrestrial planets, with a unique balance of elements shaped by its history and environment. The richness in volatile elements extends beyond sulfur. Mercury's surface contains notable amounts of sodium and potassium, both easily vaporized metals, as well as chlorine and carbon. These elements contribute to the formation of bright, reflective materials on the surface, especially in areas where impact craters have exposed fresh layers of rock. Some craters display bright halos or patches known as hollows, which appear to form when volatile substances evaporate from beneath the surface, leaving behind empty depressions. These features are unique to Mercury and are among the youngest geological formations on the planet, suggesting that volatile-driven processes may still be occurring today. The high sulfur content has important implications for Mercury's internal structure and volcanic history. Sulfur can combine with iron to form iron sulfide, a mineral that may play a key role in the composition of the planet's core and mantle. If Mercury's interior contains large amounts of sulfur, this would lower the melting point of metallic materials, allowing parts of the core to remain molten despite the planet's small size and age. This could help explain why Mercury still maintains a weak magnetic field, powered by motion within its liquid outer core. In this way, the sulfur that covers its surface may also be influencing the planet's deep interior and magnetic behavior. The abundance of volatiles also challenges traditional models of planetary formation. If Mercury formed where it is now, it should have lost its volatile elements to the Sun's heat. One theory proposes that Mercury formed farther from the Sun, in a cooler region, and later migrated inward. Another possibility is that the early solar system's environment was more complex than once thought, perhaps filled with clouds of dust and gas that shielded inner planets from direct solar radiation. Mercury's chemistry, then, becomes a record of those early conditions, preserving clues about how materials were distributed and how planets accreted. Messenger's discoveries turned Mercury from a simple, rocky world into one of the most chemically intriguing planets in the solar system. Its surface, dark and cratered, hides a subtle richness, a mixture of metals and volatiles that speaks of both fire and preservation, of heat and endurance. The sulfur and other volatile elements on Mercury remind us that even the closest planet to the Sun is full of contradictions. In a place where one would expect desolation and depletion, there is instead complexity and resilience. Mercury's strange chemistry continues to puzzle scientists, hinting that the processes that built the inner solar system were more varied and dynamic than we ever imagined. It stands as proof that even the smallest world can hold the biggest surprises, carrying within its burned and battered surface the secrets of creation's earliest light. Only 2 spacecraft in human history have ever visited Mercury, the smallest and innermost planet of the solar system. This lonely world, orbiting so close to the Sun, is one of the least explored places in our cosmic neighborhood. Its extreme environment, intense sunlight, searing heat, and deep gravitational wells makes it a difficult destination for spacecraft. Yet, despite the challenges, 2 missions have dared to approach it: Mariner 10 and Messenger. Together, they transformed Mercury from a mysterious point of light into a world of astonishing complexity, revealing its cratered surface, vast cliffs, and even signs of an active interior. The first visitor to Mercury was NASA's Mariner 10, launched in November 1973. At the time, almost nothing was known about the planet. Because Mercury orbits so close to the Sun, it is hard to observe from Earth, always lost in the glare of dawn or dusk. Mariner 10's journey was an ambitious attempt to change that. Using a gravity assist from Venus, the spacecraft became the first in history to visit 2 planets on a single mission. It made its first flyby of Mercury in March 1974, passing within 700 kilometers of the surface. Over the next year, it completed 2 more flybys, capturing about 45% of the planet in detail before running out of fuel. The images Mariner 10 sent back astonished scientists. Mercury's surface, heavily cratered and barren, looked strikingly like the Moon's. Vast plains of ancient lava stretched between impact basins and giant cliffs, now known as lobate scarps, cut across the terrain. These cliffs hinted that Mercury's crust had contracted, suggesting that the planet was shrinking as it cooled. Mariner 10 also discovered that Mercury had a magnetic field, an unexpected finding that challenged assumptions about small planets being geologically dead. For decades afterward, Mariner 10's photographs remained the only close-up views of Mercury that humanity possessed. More than 30 years passed before the next mission, NASA's MESSENGER, Mercury surface, space environment, geochemistry, and ranging, was launched in August 2004. Mercury's proximity to the Sun makes reaching it extraordinarily difficult. A spacecraft must fight against the Sun's immense gravity and shed enormous amounts of orbital energy to avoid being pulled inward. MESSENGER achieved this through a series of complex maneuvers, including flybys of Earth, Venus, and Mercury itself, before finally entering orbit around the planet in March 2011. Once in orbit, MESSENGER began an unprecedented exploration of Mercury's surface and environment. Over 4 years, it mapped the entire planet in high resolution, studied its magnetic field, and analyzed its composition. It confirmed that Mercury's core makes up most of its volume, explaining its remarkable density. It also revealed that the planet's magnetic field is offset toward the north, an asymmetry unlike any other in the solar system. Perhaps most surprisingly, MESSENGER found evidence of water ice in permanently shadowed craters near the poles, frozen in darkness despite the planet's proximity to the Sun. MESSENGER's discoveries reshaped our understanding of Mercury. It showed that this small world is not simply a dead rock, but a complex and dynamic planet with a molten core, active geological history, and chemical mysteries still being unraveled. After completing over 4,000 orbits, the spacecraft ran out of fuel and crashed into Mercury's surface in April 2015, leaving behind a legacy of knowledge that continues to inspire new questions. In the vast expanse of space exploration, it is striking that only 2 missions have ever reached Mercury. Its closeness to the Sun makes every approach a battle against heat and gravity, demanding careful planning and precision. Yet, the data from Mariner 10 and MESSENGER have revealed a world far richer than expected. Scarred, dense, magnetic, and still cooling from its fiery birth. Today, a new mission, Baby Colombo, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, is on its way to continue this work, expected to arrive in the late 2020s. But for now, Mercury remains a planet touched only twice by human technology, a distant, shining enigma whose secrets have been glimpsed but not yet fully told. The visits of Mariner 10 and MESSENGER stand as milestones in humanity's quest to understand the innermost frontier of our solar system, a place where sunlight burns bright and time seems to move to the slow, silent rhythm of stone. On Mercury, silence is absolute. It is a world without air, without wind, without the faintest whisper of sound. The planet's surface, scorched by the unfiltered brilliance of the Sun and frozen in its shadows, exists in an eternal stillness that no ear could ever break. Even if one were to stand there, surrounded by the vast and barren plains, nothing would reach the senses but the sight of endless rock and the oppressive glow of sunlight. No echo would follow a step, no crash would accompany a falling stone. Mercury is a place where sound itself cannot live. Sound, as it exists on Earth, needs a medium, air, water, or some other substance through which vibrations can travel. On Mercury, there is almost nothing to carry those vibrations. The planet's atmosphere is so thin that it is not really an atmosphere at all, but rather an exosphere, a sparse collection of atoms drifting above the surface. These atoms are mostly remnants of solar radiation knocking particles loose from the rocks below, or traces of gases released by tiny impacts. They are so few and far between that they rarely collide. This means there is no continuous medium to transmit waves of pressure. A shout, a crash, even an explosion would remain utterly silent, the energy of the sound dissipating instantly into emptiness. If an astronaut could somehow stand on Mercury, protected by an impenetrable suit from the lethal heat and cold, they would find themselves in a world defined by this profound quiet. They might see the sun rise twice, casting long shadows across the cratered plains, and watch micrometeorites strike the surface in brilliant flashes of light. But those impacts, however violent, would make no sound. Even the grinding of rock, the crumble of a cliff, or the thud of a falling boulder would unfold in eerie silence. The only sounds an astronaut could hear would be those carried through their suit, the hum of machinery, the beating of their own heart, the breath that fogs the helmet from within. This silence gives Mercury a quality unlike any other planet. On Earth, sound is constant, even in solitude. The murmur of wind, the pulse of insects, the soft movements of air. But on Mercury, there is only stillness. The vacuum of space presses close, muting every event. It is a silence so complete that it cannot be imagined through earthly experience. It is not just the absence of noise, but the absence of any possibility of sound. The sun may blaze overhead with immense power, solar wind may sweep past in waves of energy, but none of it stirs the air, for there is no air to stir. The lack of sound also means that Mercury's landscape feels unnaturally distant. On Earth, distance is bridged by sound. The roar of a waterfall, the crash of surf, the roll of thunder. These tell us that life and motion exist beyond our immediate sight. On Mercury, nothing answers back. Every crater and ridge stands isolated, unreachable by vibration or voice. The planet becomes a kind of visual world only where all experience must pass through the eyes. One can imagine the strange disorientation of moving in such a place, where every step leaves no echo, where every action seems swallowed by a vast, invisible void. In this silence, Mercury mirrors the nature of space itself. Between the planets, there is no air, no wind, no sound. Only the endless vacuum through which light travels unimpeded. Mercury, clinging close to the sun, lives partly within that same void. Its surface is the meeting point between solid rock and infinite stillness, where the energy of the sun meets a world that cannot respond. To imagine Mercury, then, is to imagine silence made solid, a planet where even the most violent forces play out in mute precision. Meteors strike, rocks crack, particles fly into space, and yet all unfolds in a soundless performance beneath the blazing star. It is a silence not of peace but of absence, the natural stillness of a world without air, where the only voices are those carried by light. Mercury's silence is its defining music, an eternal, invisible song sung in complete and perfect quiet. Reaching Mercury is one of the greatest challenges in space exploration. Though it is the closest planet to the Sun, it is far from easy to approach or land upon. The very thing that seems to make it near, the Sun's gravitational pull, makes it almost unreachable. A spacecraft heading toward Mercury must fight against the immense gravity of the Sun, constantly accelerating it inward. Unlike journeys to the outer planets, where gravity helps sling a craft outward, traveling inward demands enormous amounts of energy to slow down and match Mercury's orbit. Without careful planning and countless adjustments, a spacecraft would simply be pulled past Mercury and fall toward the Sun, lost forever in its blazing gravity well. Even when a mission reaches Mercury's orbit, landing is another story. The planet's gravity, though only 38% that of Earth's, is strong enough to make any descent dangerous, especially when combined with the Sun's influence. To land safely, a spacecraft must slow down precisely, burning fuel in a delicate balance between falling and stopping. There is no atmosphere to help with aerobraking, no air to spread parachutes or slow the descent through friction. A lander must rely entirely on engines, consuming precious fuel for every second of its journey to the surface. One small miscalculation could mean crashing into the rocky plains or missing the planet entirely. The sunlight at Mercury is another brutal obstacle. Being so close to the Sun, the planet receives up to 10 times more solar energy than Earth. A spacecraft descending on the sunlit side would face searing heat, temperatures hot enough to melt lead. The unfiltered glare would scorch metal and fry electronics unless shielded by heavy insulation. Yet just beyond the day's edge, the darkness brings the opposite extreme: nighttime temperatures that plummet hundreds of degrees below freezing. Any craft attempting to land must survive both inferno and ice, shifting between the two in mere hours as Mercury slowly rotates. The planet's surface itself adds to the challenge. From orbit, Mercury appears covered in craters and cliffs, a rugged landscape with few flat regions safe for landing. Vast ridges and deep depressions make the surface uneven and unpredictable. A lander must navigate a terrain that offers no smooth welcome, one shaped by billions of years of meteor impacts and planetary contraction. Unlike the Moon, where landing zones can be carefully chosen, Mercury's harsh lighting and limited communication windows make it difficult even to find a suitable spot before the descent. Communication with Earth is another limitation. Because of Mercury's position near the Sun, radio signals are easily disrupted by solar radiation. There are times when the Sun itself blocks all communication entirely, leaving a spacecraft isolated and unable to send or receive commands. Any landing attempt must therefore be almost entirely autonomous, guided by software capable of making instant decisions with no help from Earth. It must see, think, and act for itself in one of the most unforgiving environments in the solar system. So far, no probe has ever landed on Mercury. The closest we have come are orbiters like NASA's Messenger and the European-Japanese mission Bepi-Colombo, which have mapped the planet and revealed its secrets from above. These missions prepare the way, studying its thin exosphere, its magnetic field, and the temperature extremes that would challenge any future lander. They show us that Mercury is not just hard to reach, it is hard to endure. To land on Mercury would be to conquer heat, gravity, and silence all at once. It would mean touching a world that has never felt the weight of a machine or the echo of a human presence. The difficulty of reaching it makes it a symbol of persistence and precision, a reminder that even the smallest planet can test the limits of human ingenuity. Mercury waits, quiet and blistering, turning slowly beneath the sun, daring us to try.